Meet Gaia 20 EHK. It sits about 11,000 light-years away from us in the constellation Puppis. For years, it was a perfectly ordinary main-sequence star, burning steady and bright in the dark. Stars of this size and age are highly predictable. They settle into a long, stable rhythm, emitting a constant, flat baseline of light. They do not abruptly change their output or go dark. This is the star's visible light output. For years, the line was flat. But in 2016, astronomers spotted 3 distinct dips. Something temporarily blocked the starlight. Then, in 2021, the output became completely erratic, plummeting without pattern into a chaotic, jagged curve. A normal planet crossing in front of a star creates a clean, uniform dip in light. This ragged signature indicates something massive, asymmetrical, and messy is physically obscuring the star. When a predictable, middle-aged star is suddenly surrounded by millions of miles of rock and dust, it indicates a catastrophic, system-altering event has occurred. This chart compares the 2 signals. While visible light on the bottom axis crashes, the infrared light, the colored line, surges upward. In astrophysics, a massive infrared spike translates to physical heat. This material is glowing at roughly 900 Kelvin, or over 1100 degrees Fahrenheit. That temperature indicates the object blocking the star is not a cold asteroid or a standard gas cloud. It is an enormous field of freshly pulverized molten rock. The scale of the debris is immense. Based on the intensity of the infrared glow, the total mass of this glowing dust is roughly equal to Saturn's icy moon Enceladus. Generating this specific volume of liquefied rock requires an extreme release of kinetic energy. The only mechanism capable of this is the violent destruction of planetary bodies. These conflicting light signals show that astronomers are witnessing the immediate aftermath of 2 fully formed planets destroying each other in real time. In 2016, those first 3 dips in starlight were caused by 2 massive planets. Locked in a decaying orbit, they sideswiped each other, trading a series of grazing impacts that chipped away their outer crusts. These collisions sheared off surface material, but they lacked the kinetic energy required to generate a massive infrared heat signature. The orbits continued to degrade until 2021, when the massive planets spiraled back around and finally impacted head-on. The kinetic force of that final collision liquefies both worlds. The planetary bodies dissolve into a single superheated cloud of swirling gas, dust, and rock. This sequence, grazing impacts followed by total pulverization, provides a physical blueprint for how giant planetary impacts unfold. The debris cloud is orbiting Gaia 20 EHK at a specific distance, exactly 1 astronomical unit, or AU, away from the star. An astronomical unit is the distance at which Earth sits from our own sun. It is the habitable distance that defines our own position in the solar system. Roughly 4.5 billion years ago, a Mars-sized planet named Theia slammed into the proto-Earth at this same orbital distance. The resulting debris ring from that impact eventually cooled and clumped together to form our moon. We see evidence of this violent past in Apollo lunar samples. The jagged, composite structure is a geological relic of that original debris ring. Observing Gaia 20 EHK provides a direct view into the past, mirroring the exact violent birth of our own world and moon. Giant impacts are a universal mechanism. They are the chaotic process required to shape the final architecture of solar systems across the galaxy. In the Kepler-107 system, an impact was so intense that it fundamentally altered a surviving planet's density, leaving it far heavier than its neighbor. This process, called mantle stripping, blasts away a planet's lighter outer rock and leaves behind an unnaturally dense iron core world. With the next generation of deep space monitoring, astronomers estimate they will catch hundreds of these collisions over the next decade. At Gaia 20 AHK, the molten rock will eventually cool. Over millions of years, these tiny fragments will gravitationally attract and begin to build new planetary bodies. The eventual stability and orbital architecture required for a habitable world often begin with absolute system-destroying violence.